Alright, so today this is the chapter 3 through 4 examination, and I will be doing question 5 from the homework. And yeah, I'll be teaching you question 5 today. So we're going to start out with part A. And part A says a box of books with a mass of 52 kilograms rests on the level floor of the campus bookstore. The floor is freshly waxed and has negligible friction. A bookstore worker applies a constant horizontal force with a magnitude of 25 newtons to the box. What is the magnitude of the acceleration of the box? So for this question and for basically every single question, for every single part question of question 5, we're going to be using the formula force equals mass times acceleration, Newton's formula. And then we're just going to be switching this up to work for us so that we can solve for acceleration. So in order to do that, we're just going to divide by mass, and then the formula becomes acceleration equals force over mass, okay? And then in this question, it says the books have a mass of 52 kilograms, so mass is going to equal 52 kilograms. And then it says that the horizontal force is 25 newtons. So then force equals 25 newtons, and then we just plug it into the equation. So acceleration equals force 25 over mass, which is 52. And then if we do that in our calculator, 25 divided by 52, we get 0.48. So acceleration equals 0.48. And then acceleration is always in mass over m over s squared. All right, and then we're going to move to part B. Meters per second squared. Sorry, let me clarify that. So acceleration is meters per second squared, not mass. M over s squared. There we go. Meters per second squared. All right, so part B. It's on a new question. And this one isn't math related, but it's more like a thought experiment. So a block of cheese of a mass of 1.6 kilograms sits on a freshly waxed, essentially frictionless table. Okay, so friction's not here. And you apply a constant horizontal force of 0.50 newtons to the cheese. Select 3 external forces that act on the cheese. Check all that apply. So the forces that it gives us is friction applied, normal, and weight. So, honestly, through process of elimination, we can already say that it's applied, normal, and weight because it said select 3. And in the problem, it says essentially frictionless table, meaning friction is canceled out. But let me just go over why it's also these 3. So if we draw a little free body diagram, that's going to be the cheese, okay? And then it says you apply a constant horizontal force. So this is going to be the applied force across the surface. So it's going to go that way. That's the applied force. And then the weight of the cheese is going to be sitting on the table that it's on. So the weight is going to be down towards the table. So that's the weight force. Check both those. And then the normal force is the force of the table pushing back on the cheese. And that's what prevents the cheese from going through the table. So the normal is always going to be perpendicular to the surface, which in this case is straight up. And so those are all the forces right there. All right, so now for part C, still dealing with the cheese, it says determine the directions of these forces, which we just did. Drag the terms on the left to the appropriate blanks on the right to complete the sentence. All right, so the first sentence is the weight is directed vertically, and then there's a blank, and our options are downward, opposite, to, along, and upward. So here, let me write these out. So downward, opposite, to, along, and upward. All right, so the first sentence, the weight is directed vertically, and then there's a blank. So the weight is directed vertically, and that is downward. The weight is downward. So downward. All right, so we can cross that out. All right, the second sentence is the applied force is directed horizontally blank the acceleration of the cheese. All right, so the applied force is this direction. And that is because in the thing it says you apply a constant horizontal force. So the applied force is horizontal, meaning we're pressing along the surface. So the answer would be along. So the applied force is directed horizontally along the acceleration of the cheese because the applied force is in the direction of movement in this case, because it says that we apply the force and it moves. And acceleration is the increase of the change in velocity. So velocity moves this way and the acceleration moves this way. So the applied force is along that. And then the last blank is the normal force is directed vertically blank. And so the normal force is, of course, like I said before, from the table. So the normal force is directed upward. So upward and along. So those are all those ones. All right, now for part D, we actually get to do some math. So part D says, what is the magnitude of the acceleration of the cheese? So it's going to be exactly like problem A. We're just going to have to solve for acceleration. We're going to do that by taking the equation F equals mass times acceleration, divide by mass, and then we get acceleration equals force over mass. And then we just gotta plug it in. So the variable, the numbers it gave us is the massive, wait. Oh, where'd it go? There we go. Okay, so the mass of the cheese is 1.6 kilograms, and the force is 0.5 newtons. 0.5, 0.50, however you want to say it, newtons. So then you just plug it in. So acceleration equals force, so 0.5 over mass, 1.6. And if we plug that into our calculator, 0.5 divided by 1.6, we get 0.3125, which we can round to decimals. So acceleration is 0.31 meters per second squared. And that's that. circle. All right. Now we're going to go on to part E. And this is a new problem dealing with a game of hockey. So I'll flip the page. So, part E. In a game of ice hockey, you use a hockey stick to hit a puck of mass 0.16 kilograms that slides on essentially frictionless ice, which means there's no friction in this problem. During the hit, you exert a constant horizontal force on the puck that gives it an acceleration of 75 meters per second squared for a fraction of a second. During the hit, what is the magnitude of the horizontal force that you exert on the puck? All right, so this one is even easier because we're on part E. We're literally just going to use formula force equals mass times acceleration, and we're just solving for force. So the mass that it gave us, the mass of the hockey puck, equals 0.16, and the acceleration it gave us is 75, that's kilograms, is 75 meters per second squared. And we're just going to plug it in. So F equals m times a, F equals m, which is 0.16 times a, 75. So F equals 0.16 times 75 equals 12. So F equals 12, and then force is always in newtons. All right. Now we're on part G. Oh wait, that's not how the alphabet works. Now we're on to part F. Then we're on the G. So part F. All right. So next, part F. How does the magnitude of the normal force N due to the ice compare to the weight W of the puck? And then it gives us these different options. N is greater than W, N is less than W, and N equals W. So for this case, it's going to be N equals W. And now let me explain why. So the normal force is the force of the ice in this scenario. So we got the puck and it's sitting on the ice. Now the puck does move this way in the problem because we hit it with the hockey stick, right? We hit it and it goes that way. But the normal force is the ice, and the only force that the ice is exerting is up the normal force. And that's because the puck is exerting a weight on the ice, which is down. Now, because the puck is just sitting on the ice, it's not going through the ice, and it's not going up in the air, they have to be exerting the exact same amount of force for the weight of the puck and the normal force in order for it to just sit there. So that's why the normal force is directly equal to the weight of the puck, because it's simply sitting on there. It's not cracking through the ice. There's not any external forces also pressing down on the puck, and it's not in the air, so normal isn't zero. It's just resting on the ice. All right, now we're on to part G. So part G says, a plate of cafeteria food is on a horizontal table. You push it away from you with a constant horizontal force of 14 newtons. The plate has a mass of 0.640 kilograms, and during the push, it has an acceleration of 12 meters per second squared in the direction that you are pushing it. What is the magnitude of the net external force on the plate during the push? All right. Now for this part, net external force is just all the forces combined. That's how you. Oh no, I'm sorry. That's for the. I'm thinking of the next question. So for this question, I mean, yes, net external force is all the force combined. But as far as this question, it's actually the exact same as the last question. So F net is force. So F is F net. So F net, it's the same thing, but we can notate it as F net equals mass times acceleration, just like everything else. And in this problem, it gives us an acceleration of 12 meters per second squared. And it also gives us a mass of 0.640 kilograms. And yeah, we're just going to plug it directly in and solve. So F net equals mass 0.640 times acceleration. And yeah, and so F net equals, now we solve for that, 0.640 times 12, we get 7.68. 68, and that's 7.68 newtons, because force is always in newtons. Okay, all right. Part H. All right. So for part H, it says, what are the magnitude and direction of the friction force that the table exerts on the plate during the push? Okay. So friction force, it can be notated as, and here they're notating it as this F, that's friction force. It can also be notated as F friction. And so we have to solve for that. Now, in order to solve for that, we take F net equals all the forces that are in this problem. And all of the forces that are in this problem are F applied, and that is the applied force of pushing it along the table. All right, so that's going to be applied, F applied. And then the friction force is going to be, friction is always going to be in the opposite direction of movement. And so since the applied force and the movement is this way, the friction force is going to be this way. Now, obviously, it's going to be slightly less because we do move the plate in this scenario. If it was equal to it, then the plate would move. And so this one is going to be F friction. So we can use the formula F net. So F net equals all of them equals the sum of these forces. So F applied plus F friction. And then we just rotate this so that we're solving for friction. So we subtract F applied, subtract F applied, and then we get F friction equals F net minus F applied. All right, and then we just plug it in. So F net we literally just solved for. All right, and so that's going to be, that equals 7.68 newtons, and then F applied, it said earlier, what was F applied? You push it 14 newtons. We push it with 14 newtons. So it's going to be, yeah, so then F friction equals F net, so 7.68 minus applied, so minus the 14, and then we just do that, 7.68 minus 14, and that's going to give us negative 6.32. F friction equals negative 6.32. And that tells us the direction. The negative tells us the direction. It tells us it's in the opposite direction of the applied force. And that's why it's negative. It's because it's going against it because yeah, that's why. Okay. That is everything. That's the last one. So, hope you enjoyed, and I'll see you next time.